So in this adiabatic process, I told you about the difference between isothermal and adiabatic process. I draw the kind of a table to you. So now really the thing is, what is my final temperature in adiabatic expansion, right? Or volume change, and I want to say reversible adiabatic. So this is a reversible adiabatic process. What is my final? And then if you know your final minus your initial, that is your delta T. And this lead to delta U, Q, what, right? And this is 0, but this is once again CV delta T. This is CV delta T. Again, this is a T, and then therefore I need to know my final temperature. So let's do the math. Okay, so this math is also a nice kind of a mini exercise how this equation can be derived. So let's start with du, dq, w, and because adiabatic, that's good. Okay, so far so good. I know that. And then I'm going to say is a reversible. So this one is all of a sudden becomes not external pressure, your internal pressure times volume change. So that's good. And then what I'm going to do is, wait a minute, I think I know something about this one too. How can I write this one related to? CVDT. Okay, so I can do that. And you guys can derive this equation right now if you want. That's all I'm saying is when U is 0, it's a reversible process. And all I'm saying is your volume change, your temperature change is interrelated, right? So I can say from, if I know my initial volume to final volume, if somebody gives you my initial temperature, what is your final temperature? If this is a scenario that I need to figure it out, that's an equation. But this equation is tricky. It's not complete, and because of the following. Why? Because this pressure certainly depends on the volume, right? But does it also depend on temperature? Yes, it does, right? So I have to rewrite this equation down to nRT minus volume dV. Okay, so that's a new equation. So I need to change that into temperature and the volume in an explicit form. So now this equation becomes minus volume nRT dV. So this is your dpq equation now. You remember your second year? When you have two variables in a differential form, what do? This is the first kind of the way to say how to deal with this one. Do you remember? Huh?
Integrate both sides.
Yeah, you needed to do the integration, but before you do the integration, what is called that's right. Yeah? Separation of variables, right? That's why this course is the DPQ is a prerequisite for this. So what's the mean? Anything that depends on temperature on this side, anything that depends on the volume on the other side. Right? So finally, you got to use something that math. Why am I learning this? This is the one. So now, what happened is nothing but just temperature has to go in the other side. Right? So now CV T over dt become minus nR V over dV. Okay? And then you do now This is a constant, so I need to do the integral from my initial temperature to final temperature. I need to do the integral from my initial volume to my final volume. And then what am I saying here is C least natural law PI, right? Minus NR natural law VF. So that's mine. So if somebody give a pressure change or the volume change, and what's my initial temperature, I can exactly calculate my final temperature. And using that, if I know my final temperature, you subtract it, your initial temperature, delta T. Now you're in business to calculate all the quantity that I want to know. But I need to kind of refine this one. So this is a tricky part. So this is a negative, right? So what I'm going to do, because this equation is kind of too complicated, so the final equation that I want to drive is, what I'm going to do is I'm going to make this one positive, and then which is a NR, initial final. Right? I can just flip this, doing this, right? And then what I do is, remember, this one can go up. That can go up. So what you do now is natural log final initial temperature to the power of CV, right? Same as natural log initial volume, final volume, because I took care of the negative sign, so this is positive. And then this one is NR. So therefore, I can finally now, final initial temperature CV, initial, final, and R. And then there we go. And then what I'm going to do is I'm going to multiply this one side by NR. So I'm putting another power to do that. So this one now comes down to final initial CV NR VI DF. So that's the equation that I want to. I finally got it here, right? So this scenario, I'm going to write this equation one more time to see if we can make this one easier. So my final initial to the power of CV and R is VI. Okay, and then here now this CV and R is same as this, right? Not only that, they want to define this as a constant C. Yes, this small c happens everywhere, but in the realm of adiabatic expansion, this is a C is being defined as. Okay. So then this whole thing becomes this. Okay. And then do you know remember the cross rule here? They are constant. So what that means is, therefore, finally, this is what I've been getting. Volume times temperature to the power of C is constant. So this is your first equation that relates the volume and the temperature to the power of C, where the C is defined by heat capacity of the constant volume divided by NR, and that's the equation. So now I can predict if somebody gave volume change, initial temperature change, I can calculate my final temperature. Once again, the T, the U, Q, and stuff like that. So you can finish the flow process. So that's the one thing that